Right, could you please confirm if you can see the slides on the screen?
Yes, doctor.
Thank you. All right, so before we move on, let's just recap on what we learned yesterday. So we stopped at crystallinity of materials, right? So let's recall how many types of crystallinity do we have for the materials? How many? 3 types. Okay, Zul, thank you. So what are they? You can unmute yourself. You can write down as well. Mono, yes, thank you. Amorphous, yes, thank you. And poly, right? So they're all together 3, amorphous, polycrystalline, and monocrystalline. So what characterizes amorphous? What characterizes amorphous material? What are the main features that characterize amorphous material? What are the main features that you can tell? Anyone? No periodicity. Good. Okay. There's no specific arrangement, no periodicity. How about poly or multi? Same thing. Grains. Okay. All right. Other stuff for multicrystalline or polycrystalline? They have grains. Okay. Other keywords around polycrystalline? Reflection level. Okay. Different reflection level. You can tell by different colors. So if the grains are big enough, you can see from the naked eyes. If the grains are not big enough, you probably cannot tell the difference. You still have to go to a specific characterization in order to tell. Right? How about the third one? Mono. What characterizes monocrystalline material? What are the main features? Anyone? Monocrystalline? Orderly arrangement. Okay, good. Orderly arrangement. Any other? Do you have grain boundaries for monocrystalline? No. Okay. Why there's no grain boundaries for monocrystalline? Why no grain boundaries? Because all are in the same orientation. Yeah. Okay. Because it is single crystal to begin with, right? It's single crystal, so that means the periodicity of the crystalline arrangement of the material is infinite, right? So it goes throughout the sample, throughout the material. So that's why you don't see any grain boundaries at all. Okay, good. So today we're gonna move on to the next subtopic in the lecture, which is impurity and doping. So we mentioned briefly and we discussed briefly about doping. We discussed a little bit about intrinsic, extrinsic, but we haven't gone through the details just yet, right? So impurities can be incorporated into our semiconductor materials. Okay, so we discussed briefly about group 3 and group 5, which can be incorporated into, say, our silicon lattice in order to alter conductivity, right? So when you talk about impurities, you can divide impurities into undesired impurities and desired impurities. So the first one is undesired impurities. So the examples of the undesired impurities are metals. For example, gold, copper, nickel, iron, sodium, platinum, palladium, yeah, aluminium. So basically, when you say they are undesired impurities, so that means you don't want the metals or you don't want the impurities to be there in the first place, but then they are incorporated into the lattice somehow due to the processing or due to cross contamination, due to some other unintended incorporation or unintended mechanism. We're going to learn that later on. So you don't want them to be in the lattice in the first place. Carbon and oxygen are another examples. exception, small amount of controlled oxygen helps to gather metallic contaminants. So you don't want to have carbon and oxygen as well in the silicon lattice. But when you do the crystal growth, later on you're going to see, particularly when you learn on the fabrication processes, a little amount of oxygen does help in terms of gathering process. So gathering process here, gather. So just gather here is a verb, but then the process name is called gathering. Gathering, okay? So this gathering process is a process where you accumulate all the unintended metal contaminants in the device into a specific region of the device that you can then remove eventually. Okay, maknanya kita kumpul metallic contaminant into one passive region in the device, not in the active region, because the active region is where you want the device to operate. But in the passive region, area interactive, you can then remove all the gathered metals eventually, right? So then in this case, a controlled amount of oxygen does help in terms of the gathering process, even though generally you don't want carbon and oxygen to be in the lattice to begin with, right? But it does help. So these unintended impurities give detrimental effects on the devices. They will kill the carriers. They will annihilate the carriers. They will cause recombination. We're going to learn this concept later on. So this simply means, in essence, the carriers that you have in the device, in the semiconductor materials, are removed from the system because of recombination process. So that means, for example, if you generate electron hole pairs in your device, say in solar cells, you generate electron hole pairs from the photon absorption. You want to collect the electrons and holes eventually for to complete the circuit. But then due to this recombination process, the electron and hole recombine. They recombine balik, dia berjumpa balik, and they annihilate each other. They diminish each other, right? And this give detrimental effects to the device. Okay, extremely low impurity specifications. This is well, one of the specification that you can tell, but this one is really dependent on the devices. Okay, the level of impurity incorporation depends on your devices. Okay, semiconductor grade silicon. Semiconductor grade silicon is the purest substance known to man, known to humankind. For example, so semiconductor grade silicon is what we discussed yesterday about 9N. Okay, so the purity of 9N. So remember, what is 9N that we discussed yesterday? What does it refer to? Anyone? Yes, semiconductor grade silicon, 99.7 more nines, right? 9 of 9. So this is called semiconductor grade silicon. Semiconductor grade material lah. So tapi since we're talking a lot on silicon, so I'm going to keep mentioning about silicon, but it's semiconductor grade in nature. So this semiconductor grade is also known as electronic grade. Kalau you nampak in the references, some perhaps mention electronic grade silicon and some perhaps mention semiconductor grade silicon. They are actually referring to the same thing, which is 9N. Okay? Kalau macam solar cell tu, I mentioned yesterday 6N, right? So typically, the terminology is called solar grade. Solar grade. This is the common terminology used in the field. Okay, in the field. In the solar industry, we call it as solar grade 6N. In semiconductor industry, we call it 9N, electronic grade or semiconductor grade. So now let's talk about doping. So we're going to learn in this particular subchapter what is doping, why do we do doping, how do we do doping, and what is the end result that we expect. So for this particular chapter, I want you to check on your phone, try to do your Google search or perhaps on your laptop as well. I want you to search the first question and perhaps you'll find the next question as well together with the with the answers on Google. So can you check what is doping? And then why do we do doping? You can just Google search doping, I guess. Doping for semiconductor, because doping is for some other stuff as well, right? So try to check what is doping. So anyone would like to share what is doping? You can unmute yourself. You can also write down in the chat box. Let's explore this together. Right, anyone? What is doping? Any volunteer would like to start? Alisa Sharafana. So like to share what is doping that you found? Ada ke Alisa? Okay, Zul. Adding impurities into semiconductor. Okay, Zul said adding impurities into semiconductor. And then Fatin, doping is a technique used to vary the number of electrons and holes in semiconductors. Yes, incorporating carriers or altering the level of carriers in semiconductor. Shasha, doping is the intentional introduction of impurities into semiconductor. Okay, this word is important. Okay, the fourth word here, intentional. That means you are doing the doping, you are incorporating the impurities into the semiconductor intentionally. Okay, remember last time in the previous page we talked about unintended impurities incorporation, right? So you somehow incorporated by accident, by processing or cross contamination or whatnot. But in this case, the doping is intended, intentional. So you plan to do the doping in order to alter the conductivity of the semiconductor. So by altering the level of electrons and holes, right? Like your other answer as well. Okay, so let's go to the second one. Why do we do doping? So it's essentially in the first answer as well, to vary the number of electrons and holes, and that will alter the conductivity or the resistivity of the semiconductor, just like what we learned yesterday, right? The resistivity and the conductivity. And it is intentional, right? Okay, how to do doping? The third one. Any ideas? How do we do the doping? Perhaps in the same article that you found, with the same search. Macam mana kita nak buat doping? It's a bit on the process, but then let's just explore anyway. It's more of the 487 kind of syllabus, but it's okay. Let's just know the process a little bit briefly so that you know pretty much some background of doping. How do we do the doping? How do we actually incorporate boron or say phosphorus into silicon? How do you do that? Anyone? All right, diffusion process. Okay, thank you, Najia. Empty space diffusion is called diffusion process. Lagi, ada lagi? Some other details would you like to share? You can elaborate or you can find a completely new keyword on how to do this. Adding electron, adding holes. Okay, lagi, ada lagi? How do you do doping? Lattice diffusion, inner lattice diffusion. Yes, you're incorporating impurities into the lattice. Introducing non-equilibrium charges. Yes. Remember last time I talked to you about we're going to be in equilibrium condition, and then we can then introduce external factors such as impurities, light, electric field in order to alter the equilibrium condition, to introduce new carriers, excess carriers. Okay, ada lagi detail? Do you find any other details on how do you actually do doping? Or perhaps, Najia, would you like to elaborate on your diffusion process? How do you actually do the diffusion? Maybe in terms of temperature, how long does it take to do the diffusion? Or if anyone else can find any other keywords on how to do doping? Selective doping, yes, it can be selective as well. Okay. Nanti we're gonna learn about this p-n junction thing, but what it means essentially, okay. For example, if you want to fabricate a device, and this depends on what device do you want to fabricate. For example, if you start off with a p-type, if you start off with a p-type silicon wafer, say this one is p-type. So nanti kita akan belajar p-type and type in detail, but this one is just a brief one. So to be able to create a p-n junction later on, we're going to learn. Tapi since kita dah cover doping ni, kita sentuh sikit, right? So a p-n junction simply means in the wafer, in the p-type wafer, you need to have a region of n-type. Okay, so you start off with a p-type wafer. So that means the whole wafer, kalau you tengok dari atas yang macam bulat tu, or it can also be squared or pseudo squared, like yesterday's case. The whole thing, the whole piece is p-type. Okay, and then to be able to get a junction or p-n junction, you need to incorporate a region of n-type. So typically, how do we do that is by diffusing, by diffusion process, a very thin layer of n-type on top of the silicon. Okay, typically, tapi kita boleh buat kat belakang, boleh buat kat depan dan belakang. It can go many different ways. But the basic one is you can diffuse a very thin layer of n-type dopant, for example, phosphorus, arsenic, antimony, into silicon. And then the moment you've done this, you got a p-n junction, right? So this diffusion, okay, let me look at Zuki's reply. If we do chemical bath deposition, we add a small percentage of dopant into the solution. Will that be said doping? Yes, exactly. It can be said doping as well. So doping can be done in many different ways. So the conventional method to do doping is by bringing your silicon wafer, say p-type, the original one, into a furnace at some temperature, typically in the region of 900 to 1000 degrees Celsius. For about 30 to 45 minutes, typically. And the ambient of the furnace is filled with phosphorus source. Okay, it can be solid source diffusion, phosphorus base, or it can be vapor from phosphorus oxychloride or some other precursors. Can be done as well. So you actually send the phosphorus vapor or antimony or arsenic vapor into the furnace at this temperature for this time, and the front region will be diffused with an n-type material, forming p-n junction. So that is the conventional method to do that. But we can also do, say, by what you said, Zuki, you can also incorporate a small amount of dopants into solution, and then you can do in a chemical bath deposition on your silicon wafer or on some other materials. You can also, say, have a precursor of phosphorus. You dispense by using a pipette, for example, and then you spin coat on a p-type wafer, forming a very thin layer of n-type, and you send the wafers into the furnace for high temperature diffusion. It can be done as well. So there are so many different ways to do the doping, right? And the details you're going to learn in 487 later on. So this is just brief. Right, so the final question, what is the end result of doping? What do you get after the doping process? So jawapan ada kat sini. You can get a p-n junction, for example, or you can actually alter the conductivities of the materials by altering the levels of electrons or holes. So, for example, if you incorporate phosphorus into silicon, then you're going to get more electrons. Okay, nanti kita akan tengok nanti in the next few slides. On the other hand, if you incorporate borons into silicon, you're going to end up with more holes, right? So having more electrons means the silicon will be more negatively charged due to more electrons, and having more holes means that your silicon will be more positively charged, right? So incorporating more electrons, making it more n-type, if you like, or on the other hand, if you incorporate more borons, you're going to make the silicon more p-type. Okay. Can also alter the crystallinity to some extent. If the level of the incorporation is too small or is typical, is conventional, you wouldn't alter the crystallinity of the material. But if just too much, that will probably alter the crystallinity of the material if it's too much. Because incorporating boron and phosphorus, nanti kita akan belajar, it will somehow affect the lattice condition if the mechanism of incorporation is such and such. We're going to look into that later on. Okay. So altering conductivity, altering the majority electrons and holes in the device, and then you can alter your PN junction as well. So let's have a look at this. So okay, anyone working on FYP based on silicon wafer? Anyone? Are you doing your FYP based on silicon? Or anyone working on diffusion or conductivity or doping on your FYP? Ada ke? I'm trying to relate to what you're doing so that you understand more. So that's my point. Anyone working on... you. Zuki, is it your project?
Yeah, doctor, but I'm not doing on the doping. We
Okay.
tried before, but then we can't get tracked the dopant using the EDX. And then
okay.
One thing is we did try to make a photo detector. It's
Okay.
to
All
get
right.
the
So
resistivity, the low resistivity.
okay. Okay. So your substrate is silicon wafer, right?
No, we are like just growing on the glass, but then we sputtered a layer of metal on it, and then we tried to make a slit and grow a semiconductor at the slit to make it
Okay. So your semiconductor material is silicon or some other materials?
No, it's zinc oxide.
Okay. So zinc oxide photodetector, right?
Yeah, doctor.
Okay, all right. If, for example, if anyone working on silicon, probably you can see, kalau tak ada tak apalah, kalau you work on silicon wafer in the lab, for example, then if you want to take the wafer from the cassette, dia punya holder tu, so you can see the label on the cassette says the resistivity of the wafer is 1 ohm cm, for example. Okay, 1 ohm cm. Dia ada label lah usually. So if it's 1 ohm cm, so I'm trying to relate to this curve later on. So let's just assume that your substrate is 1 ohm cm, right? So if you talk about doping, desired, okay, intentional, tadi your friend mentioned desired. So doping is a process where you intentionally incorporating dopants into your semiconductor substrate, for example, silicon in this case. So it can be done by many different processes. Conventional doping, you can use spin coating, you can use chemical bath deposition, you can use sputtering, you can use evaporation, so many different processes, right? So in essence, the doping process gives significant effect on the electrical properties of silicon. Because we discussed in the previous page that the doping process will alter the level of electrons or the level of holes in the semiconductor materials. So if you incorporate more electrons, your semiconductor is going to get more anti or more negatively charged. Or on the other hand, if you incorporate more holes, your semiconductor is going to get more p-type or more positively charged. So in that case, it alters the electrical properties of the silicon. So a very small percentage of dopants can increase the conductivity of silicon, for example, from 0.1% to 0.00001%. Conductivity or the inverse of resistivity is directly related to doping concentration. So this point, we learned that conductivity is the inverse of resistivity in our first class. And now we know that conductivity or the inverse of resistivity is related to the doping concentration as well. Okay, so let's have a look. For example, if you have a silicon wafer, ataupun if you grow the silicon or if you grow the whatever, zinc oxide or whatever, but this one is for silicon, for zinc oxide or for some other semiconductor materials, you have to look into its own resistivity and doping curve, resistivity versus doping level curve, right? So in this case, resistivity on the y-axis and doping level is on the x-axis. Okay, Na is for acceptor, which is for p-type. Nd is for donor. Donor concentration is for n-type. Nanti kita akan tengok why. So I'm just trying to relate to these two curve, p-type and n-type. Trivalent impurity resulting in p-type, pentavalent. Yes, exactly. So trivalent impurities such as aluminium, boron, gallium resulting in p-type, silicon, and pentavalent from group 5, phosphorus, antimony, arsenic, incorporation resulting in n-type. Okay, so if you have a wafer with 1 ohm cm resistivity, 1 ohm cm, oops, sorry. So you can come to this curve. If you're using, for example, p-type wafer, 1 ohm cm labeled, you take it from the cassette, for example, in the lab or somewhere else. This is a global reference from the data. So you can already tell the doping level in the wafer from this curve. Okay, so that's the point. So you can just do, you can come to 1 ohm cm here on the y-axis, and then you go straight to the p-type on the right. Then you come down here. You come down, you can tell already. Sorry, yeah. Somewhere there. So the doping level for this particular resistivity, 1 ohm cm, is equal to about 1.5 10 times 16 per centimeter cube, centimeter minus 3. So that's the doping level. You can tell already by looking at the resistivity alone. Okay, so now let's test. What if I give to you a wafer with resistivity of 0.1 ohm cm, 0.1 ohm cm, n-type? So what is the doping level that you have in the wafer? So you look at the same curve, 0.1 ohm cm, n-type. What is the doping level in the wafer? Now you tell me. You can unmute yourself. You can also write down in the chat box. What is the doping level inside the silicon that you are working with? You only know 0.1 ohm cm. You don't know the doping level, but you trust this curve. You count this curve for your reference. So what do you get? Anyone? Any guess? Just read from the graph. It's quite simple, right? 0.1 ohm cm. Yep, go ahead.
Between 10 to the power of -7 to 10 to the power of 18. For p-type is around.
For n-type.
For n-type,
Yeah, resistivity is 0.1 ohm cm, n-type.
N-type. Oh,
Okay, dekat mana tu? Where is the location on the y-axis? 0.1 ohm cm.
it's like around very near to 10 to the power of 17.
Ah, yes, right. So you can
But
just
no,
come here.
uh,
Tak apa, it's okay. Let's just go here. 0.1 is right there, right? 0.1 is right there.
yeah.
There you go to n-type on the left curve, not the right curve. Then you go down, so that's close to 17. That's probably about 7 times 17. 7 or 8, 17, right?
16.
16,
16,
right?
I think.
16, sorry. Yeah, before 17, sorry.
Yeah.
7 times 16, sorry. Yes, 7 times 7e16 or 8e16, somewhere there, right? Depending on the exact line, because I didn't do it correctly. It's probably around 7. Okay, so 7e16. So that's how you tell. So you don't have to, when you work on a silicon wafer, for example, you don't have to really know the level of the doping concentration just yet. You can just tell by looking at the label on the cassette before you take the wafers, right? From there, you can just come to this curve, because this curve is what we call the reference, the gold standard, if you like, the gold standard for resistivity against the doping level for p-type and n-type wafers. Okay, So then if you want to go into the lab and do the measurement and do the characterization on Hall effect and whatever to really measure the actual dopant concentration, you can do that as well. But you already know by the resistivity curve to begin with, right? Okay. So what is p-type doping and what is n-type doping? So p-type doping is called positively charged doping. So the goal is to add on more borons into the silicon lattice to make it more positively charged. So holes are the primary carrier. Okay, in the positive doping or in the p-type doping, holes are the primary carrier. Why is it so? Boron is a p-type dopant, is from group 3. Okay, so that means the valence electrons is 3 bonded to silicon with 4 valence electrons. Okay, so you have to come and look at this boron incorporated into the silicon lattice. So for every bond, you can see that there is one vacancy there, right? The white area, the white dot is a vacancy introduced by boron due to its 3 valence electrons. So for every boron, there's always one vacancy introduced into the lattice. And that vacancy is the lack of electron or hole. Okay, hole is the vacancy of electron and is positively charged. So dopant atoms are referred to as acceptors, which are holes due to the presence of vacancies introduced by boron into the lattice. Acceptors have a vacancy or hole that readily accept electron from the neighboring atoms. Okay, so that means you have the more boron you have in the lattice, the more white dots or white circles you have in the lattice. So that means you're introducing more and more free holes into the lattice. Free hole into the lattice, right? This vacancy can migrate under the influence of an electric field. So these free holes forming the majority carriers in the silicon, which makes it more more p-type, sorry, because it's positively charged. So the majority carrier is positively charged, and then the silicon gets more positive or more p-type. Okay. On the other hand, if you dope your silicon with n-type impurities from group 5, like arsenic, antimony, phosphorus, antimony, Sb, okay, from group 5. So electrons are the primary current carrier, because for every phosphorus that you incorporate into the silicon lattice, phosphorus has 5 valence electrons and silicon has 4 valence electrons, and the remaining one, the one that is not bonded, will be free to move around the lattice, forming majority carriers. Okay, majority carriers will be free electrons. Okay, forming n-type dopants are referred to as donors. So dopants in this case are referred to as donors because they donate extra electron into the lattice. Kalau yang tadi p-type, we call it acceptor because it accepts, because it lacks of one electron, it readily accepts. But in this case, it has one extra electron, so it donates one silicon into the lattice. Donors have an extra electron that is able to move freely in the lattice, forming n-type silicon. Okay. So eventually, we're almost done with this. Later on, we're going to look into, in week 6 or 7, I think, we're going to look into formation of p-n junction. So p-n junction simply means you combine p-type and n-type materials together, n-type semiconductor materials together. For example, you can use p-type, the easiest one would be p-type silicon combining with n-type silicon. Okay, so this p-type silicon is probably doped by boron. This n-type silicon is probably doped by say phosphorus, for example, phosphorus at some level. Okay, so when you say you dope your material to p-type or n-type, the level of doping can really vary from lightly dope. You can lightly dope your silicon. Lightly doped typically means you dope around 10 to the 14 or so, not so high. You can moderately dope. So that means the level is a bit higher than the first one, typically around 10, 16 or 17. You can also, what do you think is the third one? Lightly dope, moderately dope, and the third one? Any idea? I think we mentioned yesterday in the class.
Heavily dope.
Heavily dope, yes. Heavily dope. Can also heavily dope. Okay. So typically around 10, 19 onwards and above. So that means if you want to have a PN junction, you can form a PN junction by combining different combination of PN. You can have 10, 14 on the P, 10, 14 on the N combined. You may have 10, 19 on the P, 10, 14 on the N combined. You may have 10, 18 on the P, 10, 18 on the N combined. You may have 10, 19 on the P, 10, 19 on the N combined. You may have 10, 14 on both sides. You may have 10, 15 on both sides. It can also be at any levels that you like, depending on what do you need to have for your devices. Okay. So if you look at well, it's quite complicated to tell on ICs because the level of doping is really different according to the layers. If you talk about solar cell, for example, solar cell is more simpler to explain in terms of the doping. If you use P-type silicon wafer and you diffuse a very thin layer of N-type, a very thin layer in this case, I mean, if you use your original silicon to be 160 micron, original silicon wafer is 160 micron, for example, in thickness. By a very thin layer, I mean just about 2 to 300 nanometer into the surface. So just imagine you have like 160 micron of a very thick wafer, not that thick, but if you compare to the 200 nanometer, it's very, very thick, right? So you just consume the first 200 or 300 nanometer perhaps of the silicon wafer to form a junction, to form N-type layer, therefore forming a junction. Okay, so this order is very, very small if you compare to the original silicon thickness. So in the silicon solar cell, for example, typically the best, the optimum doping level would be 10, 16 or 1.5, 10, 16 for the P-type, wafer. And then typically for the emitter, this layer we normally use around 2E19. For it to perform the best, right? For the conversion efficiency to be as high as possible. Because there will be effects of different doping levels. So kalau you, for example, if you use your P-type to be 1018, and then your thin layer, your emitter layer is 1019, there will be bad effects to the device. Okay. 1016 so far, but it's by far the best one as far as solar cell is concerned. But if you look at ICs, we're going to look later on, there'll be many, many layers and there'll be many, many doping levels across the device. Okay. So is it okay so far? We are done with this topic. I don't want to continue just yet. Our next topic would be energy gap. All right. So is it okay? Do you have any question to ask from this impurities and doping you're not clear with at the moment? This is just very brief. We're going to learn a lot more when we talk about intrinsic and extrinsic about doping, right? Intrinsic means pure. So that means your silicon is pure silicon, undoped silicon. Okay. For your information, if you talk about undoped or intrinsic, undoped ataupun intrinsic sama je, means it's pure, it's untouched, very pure silicon. The doping level is around 10 to the 10. 10 to the 10. Okay. Undoped. If you dope, then it can be lightly doped, like 10, 14 or 15 or 16 or 17 or 19. or it can be beyond that, right? So, but undoped is 10 to the 10 to the 10 for your reference. So we're going to learn this a lot more in intrinsic versus extrinsic. Intrinsic means pure, doping level is 10 to the 10. Extrinsic means dope at low level, moderate level, and high level. Okay. So any questions? Okay, okay. Lightly dope is how much? Okay. Lightly dope is typically around 10, 13, 10, 14, 10, 15. You can still say lightly dope. 13 to 15 typically. If you go below 13, it's almost intrinsic. It's not exactly intrinsic, but then it's almost intrinsic. And if you measure the resistivity, it's going to be very, very high because it's almost undoped. Because undoped is 10 to the 10. So
Doctor,
Mhm.
so moderately dope is 15 to 18, is it?
Normally people say moderate dope is about 15. You can say starting from 15, but typically people say about 16. But there is no, for this lightly dope, moderate dope, and heavily dope, there is no what you call a clear-cut answer as far as the figure is concerned. But typically we mentioned the region of lightly dope is 14 and below, and starting from 15 we can say moderately dope already up to about 17, and then the moment you exceed you get 18 onwards, you can say heavily dope already. Okay.
Understood, doctor.
Okay, any other questions for others? Okay, can you follow so far? Is it easy so far? So far okay, okay, all good. Okay, if there's no question, then that's it. I'll see you tomorrow 10 a.m. Yeah, bye bye, take care, assalamualaikum.
Doctor, I want to
Yeah,
ask,
yes.
do we need to take attendance?
No, you don't have to. You don't have to. I can just extract your attendance from your WebEx login
Oh, okay, okay. Thank you.
for every class. I can just extract the report for every class. Okay?
Okay, doctor. Thank you, doctor.
All right then. Okay, bye-bye. Take care. Assalamualaikum.
Thank you, doctor. Bye-bye.
No worries.